for Germany. The concept of the potential is a difficult concept. Actually, you cannot ask what is the potential for a country. You have to ask what do you take as the, or what do you take to be the potential for a given country. Normally, or in many books, you will find that there are different concepts of potential. There's first the physical potential. Physical potential means something what we saw before, the naturally given energy flows. Now you can calculate what is the solar energy reaching the Indonesian land area over 1 year, and you can say, okay, this is my physically given solar resource. Okay, this is a large number, and it's not a useful number because you cannot use everything of this energy that reaches the land area of Indonesia. So there is another concept of potential, which is the technical potential. What can I use technically of, for instance, the solar radiation that reaches Indonesia? Okay. Yeah, technically I can use a lot, but maybe it will be very expensive. So there's another concept, the economic potential. Then you take into account that it may be very expensive to harvest solar energy in one place, but much cheaper in another place. So maybe you will put a PV panel in the cheap place, but not in the expensive place. And then there's a fourth concept of potential, which is the sustainable potential. What does this mean? Well, you can identify your physical resource, the energy flows. You can identify the amount of energy you can harvest technically. You can calculate the costs of this process of harvesting the energy. But then you have to ask additional questions. For instance, if there's a river, do I really allow to build a dam in this river? Or are there some natural protection arguments against this? Or do I accept wind turbines near the city? Or do I allow land usage for PV plants? Or how much space do we want to sacrifice for biomass production for energetic uses? There are a lot of questions which have to be answered politically. It's not a question of facts. So the potential, for instance, of wind energy in Indonesia or bioenergy in Indonesia, the potential, to identify the potential is only partially a question of facts. It's basically a political question. That's why I say it's a cost optimization problem under politically defined frame conditions. I first have to put my political framework and have to define, okay, I can build a PV plant not only on the roof but also on the ground, or I cannot. These are big discussions we have in Germany every day. Okay, then we have to ask, of course, how expensive is it to generate the electricity? I will speak now only about electricity. Yeah? In the next 45 minutes. What are the levelized electricity costs? So this is the diagram we saw before. You can identify the costs. How much does it cost to generate 1 kilowatt hour from PV, 1 kilowatt hour from wind, whatever. And you will give a certain priority to the cheaper technologies. But there are two problems in this. First, costs will change in the future. All these technologies are still in development, and the costs, they change from year to year. Normally they go down. The costs go down because these technologies become more mature, the markets become bigger, there are some learning effects, so normally the tendency is that the prices come down. This is an estimation. Well, to speak about future prices is always a bit difficult, but this is the most serious cost estimation I found for 2030 in Germany. So in this case, it is considered that wind energy will be the cheapest. It's already now the cheapest, but then it will be absolutely the cheapest manner to generate electricity, also cheaper than coal power plants. Photovoltaics will be also quite competitive and in the range of the cheapest fossil fuel-fired power plants. Offshore still will be more expensive, and biogas will not change so much. Okay. Yeah, this is the first problem. Prices will change. You have to take this into account. The second problem is to choose the cheapest generation technologies does not mean that the complete system will be the cheapest. These are just these levelized electricity costs indicate how much does 1 kilowatt hour cost from my PV panel. How much does the kilowatt hour cost from my wind turbine. But at the end, we need a cheap energy supply system and not just isolated, cheap electricity generation systems. What do I mean? Well, take for instance the temporal distribution of the resource. If we are speaking about renewable energy resources, we are speaking about resources with very different characteristics, very different qualities. For instance, you have resources that are always available, like hydropower in many cases. You have other resources that are not always available, like solar energy, wind energy. Among the fluctuating resources, you have some which have regular fluctuations and other that have more aleatoric fluctuations. Strongly regular, for instance, is tidal energy. In many cases also bioenergy. You have the annual, in Europe for instance, you have a strong annual rhythm. Yeah, this is a strongly regular pattern. On the other hand, wind is quite strongly aleatoric, not regular. Solar energy is in between. It's a bit regular, a bit aleatoric. So these are very different qualities. You have to take this into account when you construct an energy supply system. Of course, it's better to have a constant source. It's better to have a source which has regular fluctuations than irregular fluctuations. And if you have irregular fluctuations, it's better to have the possibility to predict the fluctuations. But there also you have quite different conditions among the different resources. To predict wind energy is not so easy. Maybe for the next day, but what happens in 3 days? That's not so easy. Another aspect, speaking about the temporal distribution of the resource, is the coincidence of the resource and the consumption. This shows, this is quite interesting, this shows the daily load in the electricity system in Germany. So we have the peak at noon. You have the peak in the evening. In Germany, it's at noon. This is a summer day, and this is a winter day. This is a summer day without wind, and this is a winter day with much wind. The green columns is the wind energy, which is delivered by the wind turbines distributed over the country. The yellow columns is solar energy, and the black or gray columns indicate the energy generated by all other generation units. That means fossil fuel-fired power plants, and also hydropower is there included. What is interesting here is that the solar energy just cuts the peak at noon. This is a very, very nice condition we have. Here it's different. You have to take this into account when you design your energy supply system. Okay. Another important point is when you select the sources you want to use is power density and spatial distribution. When we speak about renewable energy resources, then we speak about resources that in many cases are spatially distributed. More or less. Take solar power, you have a maximum power density of about 1000 watt per square meter. This is the highest you can get. Here you don't get it, because the atmosphere is not so transparent here. But maybe in eastern Indonesia you can get it. And when you are on high mountains, you can even get a bit higher values. The average of the solar energy is 165 watt per square meter. Bioenergy, on the other hand, has a much lower energy density per area, about 1 to 3 watt per square meter. This is the power density of bioenergy. The heat flow of the Earth the average is about 0.06 watt per square meter. Several orders of magnitude lower than bioenergy and even more than solar energy. On the other hand, you have forms of concentrated solar energy. For instance, wind. Wind is concentrated solar energy. Water streams, concentrated solar energy. Waves, concentrated solar energy. That's why they are so interesting, because with smaller systems you can harvest larger amounts of energy. Okay, this is another important aspect to take into account when we design energy supply systems.